Algorithms for generating combinatorial objects. Most important types of combinatorial objects are permutations, combinations, subsets of a given set. Whenever you have solved this traveling salesman problem and knapsack problem using brute force design technique, there for traveling salesman problem you have generated all n-1 permutations, and for knapsack all possible subsets of n items. Assume the set containing n elements, then the n element set can be interpreted as a1, a2, etc. an. Then what would the decrease by 1 technique suggest for the problem of generating all n factorial permutations? We'll see now. The first approach is bottom-up approach. Here, if you know the solution for n-1 factorial, with that you can find the solution for n factorial. We'll see how this can be solved. Assuming that the smaller problem is already being solved, then we can get a solution for larger one by inserting n in each of n possible positions among elements of every permutation of n-1 elements. There are two possible order of insertion. One is from left to right, other one is from right to left. Now here, start with 1. Now for one element, the only one permutation is 1 itself. When there are two elements, two permutations are possible. That is, start inserting 2 from right to left. So 2 here and then 2 here. So with that, 2 permutations are possible, 1, 2 and 2, 1. Then for these two, insert 3 from right to left. We'll see when you insert 3 from right to left for the first permutation 1, 2. These are the 3 permutations possible. 1, 2, 3, then 1, 3, 2, then 3, 1, 2. So these are the 3 permutations for 1, 2. Again, when you insert from left to right for this, so 3, 2, 1, 2, 3, 1 and 2, 1, 3. So with that we have generated all possible 6 permutations. How? Because already you know the solution for 2 factorial by inserting third element from right to left for the first permutation, and for the second permutation left to right you have generated all possible 6 solutions. This way of generating all possible permutation is called bottom-up minimal change requirement. So because here each permutation is obtained from the previous one by exchanging only 2 elements. Here 1, 2, 3 here is there. So look at here, when you interchange these 2 elements, you are getting the next permutation. Again when you interchange these 2 elements, you are getting the next permutation. So in general, assume all permutations of 1, 2 up to n-1 are available, then you insert nth element in 1 to n-1 n positions from left to right, then switch direction every time a new permutation of 1, 2 up to n-1 is processed. So this is how you can find n factorial. This order satisfies minimal change requirement, but in order to find this n factorial, you need to know n-1 factorial. This is tedious task and which will take lot of space. So one more method is available to find all possible permutations that we'll see now. Before that, I discuss what is mobile integer. Associate a direction with each component k in a permutation. Look at here, 3 is associated with the arrow and 2, 4, 1. And 3 is pointing, the arrow of 3 is pointing to 2 which is smaller than 3. So now 3 is called mobile integer, and even 4, arrow of 4 is pointing towards 1. That's why it is called mobile integer. The component k is said to be mobile if its arrow points to a smaller number adjacent to it. 3, arrow of 3 points to 2, which is smaller than 3, that's why 3 is called mobile integer, and arrow of 4 pointing to 1, which is smaller than 4, so that's why it is called mobile integer. Here 3 and 4 are mobile integers, and 1 and 2 are not. Now we'll see how to generate all possible permutations by using Johnson-Trotter algorithm. Here n is positive integer, and list of all permutations you are going to get as the output. Initially, the first permutation, that is 1 to n, is to be initialized with the arrow pointing towards left. You are required to do these 3 steps while there exists a mobile integer k. Find the largest mobile integer k. The second step, swap k and the adjacent integer its arrow points to. Then reverse the direction of all integers that are larger than k. This is the procedure. Now we'll see for 3 elements. So here 1, 2, 3. All these 3 elements is to be initialized with the arrow pointing towards left. Now in the first step, what you are required to do is, you are required to find the largest mobile integer k. Here the largest mobile integer is 3. Because 2 is pointing to 1, 2 is also mobile integer, and 3 is also mobile integer. So here 3 is larger. Now once you find the larger integer, what you are required to do? Swap and call that as k. Now swap k and the adjacent integer to which arrow points to. Now 3 is pointing to 2. Now 2 and 3 is to be interchanged. So with that you will be getting this permutation, and you don't find any element larger than this 3. So no need to change the direction. Again 3 is the mobile integer pointing to 1. So interchange these two. With that the resultant is this. Now here 3 is not mobile, 1 is not mobile, but 2 is mobile element because it is pointing to the smaller element. Now interchange 1 and 2. When you swap 1 and 2, this is what you are going to get. Now here you are finding the element larger than 2. So change the direction of 3. Change the direction of 3. With that the resultant permutation is like this. In this 3 is mobile integer because 3 is pointing to 2. Now exchange these two elements. When you swap these two elements, the resultant is this. Again 3 itself is the mobile integer. Swap 3 and 1. So with that you'll be getting 2, 1, 3. Look at here. 2 is not pointing to any element and 3 is also not pointing to element, but 1 is pointing to 2, but it is larger than 1, so this cannot be mobile integer. With that, so the control will come out of the loop because there does not exist any mobile integer. So like this, the Johnson-Trotter algorithm will work. So now the assignment for you is generate all possible permutations for 4 elements by applying both the methods. One is by bottom-up approach. The second one is Johnson-Trotter algorithm. We'll see how to generate all possible subsets of a given set containing n elements. Now here also you can find the solution by decrease and conquer technique. That means if you know already all possible subsets of n minus 1 elements, then you can find all possible subsets of a set containing n elements. So initially, look at here, the cardinality of the set is 0. Then only one possible subset is null set. Then you are required to generate all possible subsets of one item, that is A1. For that, write the subset, whatever subsets you have in the previous iteration as it is. For that, add the element A1. Look at here. So A1 union null is A1. The new subset is A1. Next, to generate all possible subsets of two items, write in the previous iteration whatever subsets you got as it is. Then include A2 for all the subsets. A2, when you add to this null, then the resultant is A2 itself. A1 union A2 is A1, A2. So these are the four possible subsets for two items. Again, here, to generate all possible subsets for three items, first write in the previous iteration whatever subsets you got as it is. Then add the third element to all of these subsets. A3 union null is A3, then A1 A3, then A2 A3, then A1 A2 A3. So these are the subsets for three elements: 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. 2 cube, right? So if there are n elements in a set, how many subsets are possible? 2 power 1, 2 power n. 2 power 0 is one subset, 2 power 1 is 2 subsets, and 2 square 4 subsets. Here 8 subsets. So this is how you can generate all possible subsets of a given set if you already know all possible subsets of n minus 1 set. Okay, so this is how you can find the solution, or you can generate all possible subsets by decrease and conquer technique.